According to the cloud. Confirmed. Okay. All right. So today is our final class meeting before our next exam on Monday. I wanted to spend a few minutes at the beginning talking about what you can expect for your upcoming exam. A formal announcement will be, of course, sent out by tomorrow or this Friday. But regarding module exam 4, we, of course, know logistically it's identical to all the previous exams. So, of course, you show up here by 12 p.m. You'll have the entirety of lecture and lab to complete the exam. The module exam is in total 50 points. While we're on this, let's just clarify something about the extra credit. Because the exam is worth 50 points, you'll actually be getting 5% added to your score if you submit the extra credits. If you submit the extra credit, the simple reason for this is if I had added 5 points added overall, 55 points would mean that you could potentially score up to 110%, which of course just artificially inflates everyone's grade. Versus with the 50 points, you'll of course get your flat 100 and then gets added a 5% to it, 105. That way we all know exactly what we're expecting with the point system. Now, of course, the extra credit is due the night before the exam, Sunday night. The announcement will remind you of exactly what topics we covered, but there are in total 4 extra credit opportunities. Under these 50 points, the exam is divided into 2 sections. 30 points of the exam is based on drawing. You'll specifically be asked to draw 6 Vesper geometries. Each of which is worth 5 points. As a reminder, way back when in our drawing topic, in our Lewis structures topic, I had promised you way back then, the questions that will appear on your exam will come from the worksheets. In other words, what if you have completed the worksheet in full, then you have done every single question I could potentially ask you at least once. Of course, if you remember, the concept of drawing can be very complicated. So instead of trying to tell you what could come, which is a bit too exhaustive, it's easier to say that, well, your 6 questions will be from the 15 that you've been given on the worksheet. So as long as you practice that worksheet in full, that drawing worksheet, you are prepared for any drawing questions I can throw at you. The remaining 20 points of the exam are all multiple choice questions. Of course, each multiple choice question is worth 1 point. So all of them in total is 20 points. The multiple choice section then divides up the remaining topics: thermodynamics, today's or at least this last topic, Equilibria, and of course, acids and bases. Of those multiple choice questions, some of them will be outright explicit math questions, such as asking you to calculate things. Some of them will be more content-based. An example of what I mean by content-based is I could ask you, is an exothermic reaction positive or negative? Where, of course, you're not being outright asked to calculate something. It's just a matter of, do you understand and can remember? Of course, in this case, an exothermic is, of course, negatively charged. Not negatively charged, is a negative value overall. But that's what I mean by some of the multiple choice questions will be content-based and some of them will be math-based. So not every single question here will involve use of your calculator, of course, but most of them will. I don't remember the exact split up. Now, on that guise of the math part of it for the multiple choice questions, each person has been provided with the exact formula sheet that will be included as part of the exam worksheet. If you do notice that I missed an equation that I did promise I would give you, please let me know sooner rather than later. I'm pretty confident I got all the equations, but if I did honestly miss something, I'm more than happy to update it on my end, post an update in the Discord, and give you that updated worksheet on your actual exam. But as of right now, this will be the exact formula sheet you will be given. There are a couple things, of course, you should be able to notice. We have up here in green, these are our thermochemistry based topics. On this right, thermochem. In green, QC, of course, has to do with equilibria. And then a couple of these other equations are all having to do with acids and bases. And then the final set of equations given here are just our general stoichiometry-based equations. Of course, since we did cover the topic of titrations and neutralizations under acids and bases, you may, of course, be asked questions about the roadmap. So the roadmap will be provided as part of the exam booklet. You will, of course, in addition, get a copy of the periodic table. It should be reasonable to assume that I did not print that out specifically today, but you will be given a copy of the periodic table as part of your exam. As always, I write the exams to take approximately the same amount of time in lecture, an hour and 15, but you will be getting the entirety of lecture and lab to complete the exam. On average, I wouldn't necessarily be surprised if the average time taken is between an hour and a half to 2 hours. This is not necessarily a long exam because it's so complicated. It's just a long exam because of how many topics are, of course, tested. I do recommend trying to study all of these topics sort of equally. Don't assume that, there will be a very popular topic in the multiple choice section. Of course, there is an entire 30-point question dedicated to drawing. So the exam is heavily weighted on Lewis structures and Vesper geometries. But of the multiple choice questions, I believe they're fairly evenly split. It's like 4 to 6 questions per topic. Does anyone have any questions about the exam? Logistically, it matches all the other exams so far. So if there are any questions that do come up, do let me know. I'm more than happy to answer them. Feel free to message me over email or on Discord. With that, I would like to now turn our attentions to today's workshop on Equilibria. We know how this works already. We'll be doing some questions with you as professor guided questions. And then after we do some together, you'll get some assigned. You'll also get some extra credit questions. So I'd actually like to start with problem 1. And maybe before we start specific questions, let's just do a quick recap of Equilibria, or at least the most important bits and pieces that we all want to understand, at least heading into today's workshop. So regarding chemical equilibria, we talked about how when we previously referred to the change of reactants and products over the course of a reaction, way back when in kinetics, we had drawn this graph that at the time got the point across of at the start of the reaction, we expect 100% reactants. At the start of the reaction, we expect 0% products. And by the end of the reaction, we expect those numbers to flip such that there is nothing but products and absolutely little to no reactants at all. This graph, of course, worked way back when in kinetics because it, of course, allowed us to understand rate laws and the equation of the line. But in reality, when real data is plotted, we actually don't get that nice linear slope. In fact, what we get is somewhat of a curve. Not only that, the curves no longer intersect as they did on the left. In fact, they curve and meet each other after some time. Now, the big discrepancy here is a big idea that instead of products going all the way to 100%, instead of reactants going all the way to 0%, in truth, what happens is something of around a 50-50 ratio. In other words, what we see here is an equilibrium between the reactants and products, such that there are as many reactants as there are products. This is what led to the idea of chemical equilibrium, which is a state that is established when the rate of formation of products is equal to the rate of formation of reactants. In other words, the products are being formed at the same rate that the reactants are being formed, that the reverse reaction is taking place. This is what's called a form of dynamic equilibrium. Dynamic equilibrium, the analogy I likened it to, is a classic game of tug of war, both teams on opposite sides of the rope pulling with as much strength as they can. Of course, in the game of tug of war, if both sides are evenly matched, then the rope isn't moving. Of course, objectively speaking, both sides are pulling with as much strength as possible. The issue is that they're evenly matched such that the rope isn't moving as a net effect. Equilibrium can be thought of as the same way. In other words, A is forming B at the same rate that B is forming A, such that visually or overall, there is no net difference. This is what's known or described as a reversible reaction. Now, one very easy example to explain the concept of reversibility is the N2O4 change up to 2NO2. This is not necessarily a case where the chemical is broken up into pieces, but rather a slight rearrangement. Instead of it potentially being two nitrogens on the outside, who knows what this Lewis structure could look like, they end up breaking apart to result in 2NO2. Of course, the idea here is as much as they're breaking up, they can get back together to form N2O4. This example is what led us to understanding what exactly is equilibrium and how do we know if a reaction is at equilibrium. That then led to something known as the reaction quotient. The reaction quotient, here labeled as QC, is defined as the concentration of products divided by the concentration of reactants raised to their stoichiometric ratios, where for a generic equation A plus B to give us DE, the reaction quotient is defined as the product of the D and E concentrations divided by the product of the A and B concentrations, all raised to their individual stoichiometric values. So in truth, all we need to calculate reaction quotient is number one, the balanced equation, and number two, some concentrations to accompany it. So for example, in the equation that we looked at, N2O4 to 2NO2, to calculate the reaction quotient, it's as simple as putting the products, in this case, the NO2, divided by the reactants, the N2O4, raised to their stoichiometric values. The NO2 is raised to 2 because there's a 2 in front of it. The N2O4 is raised to 1 because, of course, there's implied to be a 1 in front of it. And anything raised to the 1 is itself, so we don't necessarily need to write that 1. The thing about equilibrium is that at a given temperature, remember we assume on paper, unless specified otherwise, all reactions occur at room temp. But at a given temperature, every reaction will have an equilibrium constant. This equilibrium constant is either given the symbol KEQ. You might also see on some online resources or your textbook KC. They both mean the same thing. They can be interchangeable, but I most frequently use KEQ. You see, it's not enough to calculate QC. You have to actually compare that reaction quotient to the constant to determine if a reaction is at equilibrium. In fact, if the reaction quotient is equal to the constant, it is at equilibrium. If the QC is not equal to the equilibrium constant, then it is not at equilibrium. But the thing about these reactions is that equilibrium is a very desirable state. In fact, if a reaction is not at equilibrium, best believe it will do whatever it can to get to equilibrium. In fact, if QC is less than the constant, then you will favor the product side. In other words, you will favor the forward direction to establish equilibrium. If the reaction quotient is greater than QEQ, then you will instead favor the reactants. That is, you will favor the left direction, the reverse reaction overall. So not only are we able to calculate the equilibrium constant, not only are we able to determine if an equation is at equilibrium, we can predict what direction the reaction will favor to establish equilibrium. Here in this example, here we have the breakdown of SO3 into SO2 and O2, and I have provided you with the equilibrium constant. FYI, the equilibrium constant is unitless, so it's just a flat number. You're told at a specific time, so at 3:50 p.m., the concentrations are as follows. The question simply asks, is the reaction at equilibrium? Well, ultimately, to determine if it's at equilibrium, remember, it's just asking, is it at equilibrium? So technically speaking, your answer will be either yes or no. You have to calculate QC and then, of course, compare it to KEQ. To calculate QC, it's the products over the reactants raised to their stoichiometric values. We plug in those numbers and we calculate QC. Here in this case, QC is equal to 0.01. This is clearly a situation where it is not at all equal to the constant. Based on that alone, it is not at equilibrium. We can, in fact, glean more information. The fact that it's not at equilibrium simply tells us, well, the reaction will want to establish equilibrium. Equilibrium is a desirable state. So when asked, what direction will the reaction favor to establish equilibrium? There's, in fact, two methods you can take to determine this. Both of them are just logical assumptions. Number one, you can remember the explicit rule I gave you, which is that if QC is less and the equilibrium constant, we will instead favor the product side. In other words, we will make more product until we hit equilibrium. The other way to do this is a little bit more of a visual tool. It's my preferred tool. You would draw a scale from negative infinity to positive infinity. Smack dab in the center, we just write our KEQ value. And on the scale, we would place where our QC is. In this case, QC is left. It's less than 0.1. Visually speaking, this tells us we need to advance to the right to get to KEQ. If we favor the right side, we actually favor the products. Both methods lead you to the same answer, favor the products, favor the right side. But the approach taken to get there is up to you. There are a few considerations when it comes to reaction quotient. One of the big rules, or in fact, the biggest rule, is that no solids or liquids are included in the calculation. This isn't because they're not concerning. In fact, they're too much of a concern. Solid state chemistry and liquid state chemistry is entirely too complicated for this class. So it's easier to just ignore them in their entirety when it comes to equilibrium. To the point where when it comes to equilibrium, only gases and aqueous species are included. If you'd like to learn more about how solids and liquids affect equilibrium, then that is a concept covered in inorganic chemistry, which is a class after OChem. It's generally an elective course, so you may or may not need to take it. To prove such a point, we carried out another question. This is the breakdown of carbon monoxide into carbon and CO2 gas. I've told you at a specific time, here are the concentrations, and asked, is the reaction at equilibrium? To calculate equilibrium, it's the products divided by the reactants. But the first thing you should immediately notice is that one of the products is missing. Which one is it? It's specifically the carbon. Why is it missing? Because it's a solid. Solids are not included in our calculations or our conversations. They're outright ignored. The other way you could have reminded yourself of this is of the values given to you, I did not give you any information about the carbon. That is another way you could have been told, hey, this is not included at all. Upon calculating the QC, we were able to determine that this was not at equilibrium. And of course, we drew our visual scale to tell us that this would favor reactants, aka to the left. To understand a little bit more about KEQ, it's important to understand, well, number one, we already went over that, it's unitless. Number two, KEQ does not correlate with speed. Fast reactions can have large KEQs, but simply having a large constant does not necessarily mean the reaction is fast. Having a small KEQ does not mean that the reaction is slow. It is just a reflection of the concentrations and the stoichiometric values. We also went over some different ways that KEQ can be manipulated mathematically. for a standard reaction of A to B, if assuming KQ is 100, the reciprocal, B to A, is the reciprocal of the KQ, 1 over 100. If you multiplied the equation by 2 or 3 or whatever, then it would be raised to that power. So for example, if we had 3A forming 3B, this would be 100 cubed. Finally, KEQ is temperature dependent. Now, one thing that I didn't mention on Monday's lecture about this is a very small, historically proven theory, or fact actually, which is that most reactions are reversible. Most of them are. And when I say most of them, I say at least, let's say more than 90% of reactions are reversible. In fact, there's only a few reactions that are truly irreversible. Now, remember the idea of reversibility is it can go in either direction. Think of, for example, ice. Ice melting, ice melts into liquid water. But what can you do with that liquid water? You can put it right back in the freezer and get ice again. This is an example of a reversible reaction. It can go in both directions. You can melt ice, you can freeze water. But think about something like burning a match. When you light a match on fire, it of course disintegrates into ash. You can't reform the match. In that case, that is what's known as an irreversible reaction. So most reactions are in fact reversible. One of the ways that we indicate this reversibility is with use of these signs. So most reactions we've encountered should have accurately had these signs to indicate reversibility. That is what led to our discussion of Le Chatelier's principle. Le Chatelier's principle broadly describes that if a reaction is at equilibrium, in response to changes of that equilibrium, the reaction shifts predictably. In other words, we talk about how reactions love to be at equilibrium. When they're at equilibrium, they're happy. If something happens to the reaction that kicks that equilibrium out, the reaction will, pardon the pun, react to reestablish equilibrium. That then led us to our different conditions. I won't go over it in full detail, but I'll just quickly talk about the first two columns. If we add a reactant or product, the reaction will shift away from that reactant or product. If we remove a reactant or product, we shift towards that reactant or product. We can say the same thing about pressure as well as temperature. We'll go over a question specifically about Le Chatelier's principle, so I'll go back over this table when we get there. But as of right now, does anyone have any questions before we jump into the workshop? Yes, Prop. This table will not be provided as part of the exam. You will need to know it / memorize it. Okay. Okay. And of course, as a reminder, this page right here was just an example of Le Chatelier's in theory, in application. This isn't a reaction I necessarily require you to memorize, but I could ask you on the exam, hey, which of the following conditions could lead to a maximized amount of product, right? Just as we saw here, how we could analyze the Haber-Bosch process. All right, let's start with 2 questions from problem 1. We're going to do A and B together. The question simply states, provide the KEQ expressions for the following unbalanced reactions. Okay, so we're not actually being asked to calculate anything. We just want the expression, what the equation looks like, and we're outright told that the given expressions are unbalanced. So the very first thing we want to do is, of course, balance the reaction. So starting with the first equation right here, we have 2 hydrogens on the left, we have 1 hydrogen on the right. No big deal, we'll just put a 2 in front of it. Hydrogen is now balanced. We have 2 iodines on the right. I'm sorry, we have 2 iodines on the left. And sweet serendipity, we have 2 iodines on the right as well. So the equation is balanced as written. Now, we just need to provide the KEQ expression, which is defined as the products. In this case, there's only one product, HI, divided by the reactants, H2 and I2. We're not done yet. All that's left is to, of course, reflect those stoichiometric values. There is a 2 in front of the HI. That's what tells us HI will be squared. There is nothing explicitly written in front of H2 and I2. That's, of course, implied to be 1. That means that we would put those powers to the 1. But, of course, anything to the 1 is itself, so we can leave it as is. With that, we've, of course, completed providing the KEQ expression for part A. Now let's try part B. Looking at part B, just looking piece by piece to balance the reaction, there is 1 nitrogen, 1 nitrogen. 4 hydrogens on the left, 4 hydrogens on the right in total. 1 chlorine, 1 chlorine. So the equation as written is balanced as is. So all that tells me is I got to put my products on top, NH3, HCl, all over my reactants, which in this case is just a single NH4Cl, all raised to the powers of their stoichiometric values, which is just 1, 1, 1. And I would be correct, right? No, I've made a mistake. What mistake did I make? I put a solid in the expression. See, I've defined for you here in the equation that NH4Cl is solid. That alone is what tells us it should not be included at all. So I'm just going to erase that bottom fraction, the bottom denominator. So this is it. Our KQ expression isn't even a fraction. It's just multiplying the 2 products together. So yeah, we're expecting the expression to be a fraction, you know, something clearly on top, something clearly on the bottom. But in this case, it just so happened to work out that we would put nothing on the bottom because it's a solid. Do we have any questions from problem 1? Okay. I would like to do 2 questions from page 2. I'm going to put a highlight over that. I'm going to do the top left and the bottom left. All right. We're given an equation. We're given the equilibrium constant. And we're told at 1:45 p.m., the concentrations of the chemicals are as follows. We're being asked, was the reaction at equilibrium? And if not, which direction will the reaction proceed to reestablish equilibrium? So we can split this up into a formal A and B. We know that to answer the question of whether or not the reaction was at equilibrium, we have to calculate QC. QC is equal to the products, in this case NO2, divided by the reactants, in this case N2O4, raised to their stoichiometric values. Once we, of course, identify the expression, it just becomes a matter of plugging in. NO2 is 0.2 squared. N2O4 is a simply 2. We're going to take a second. We're going to plug this into our calculator. On top, we have 0.2 squared. On the bottom, we have 2. Looks like our answer overall is a flat 0.02. We then compare this number to KEQ. It should be very quickly obvious that these are not the same number. All right, this is 0.2, this is 0.02. There's an extra 0 in our calculated answer. That fact alone is what tells us the reaction is not at equilibrium. Remember, all you need to calculate the reaction quotient is the balanced equation and a set of concentrations at whatever time you're investigating. What this tells us is that the reaction, at least at 1:45 p.m., is not at equilibrium. So then we answer part B. If the reaction is not at equilibrium, which direction will it proceed to reestablish equilibrium? To do that, we compare the two. As I pointed out before, I like drawing my visual scale, which is quite literally mapping from negative infinity to positive infinity. Smack dab in the center, I would just generically write my KEQ. This is 0.2. Doesn't need to be perfectly drawn to scale. Remember, this is just a visual tool that's helped to identify which direction the reaction proceed. Hopefully, we recognize that 0.02 is smaller than 0.2, which means it's going to be actually over here, 0.02. Again, it doesn't need to be drawn to scale. I just put it on the left. I could have put it right here. I could have put it all the way out here. It doesn't matter, but it's clearly on the left. This visual tool tells me that to get to KEQ, I am going to favor the product side. Another way of writing this is that it will favor the forward reaction. Two equivalent answers telling me the same thing. It will favor the right direction. Do we have any questions on this reaction, N2O4? Yes, Prop. Exponent. Oh, you mean this two right here? That is because the stoichiometric value from the equation is a 2. That is what tells us that we need to square it. Similarly, there is a 1 in front of the N2O4. There's a 1 here, but we don't traditionally write 1 because anything to 1 is itself. Any other questions on this reaction? Okay, let's try the bottom one now, the bottom left. This question says, with a given equation at equilibrium, okay, so we're actually being told outright that the reaction is at equilibrium. The concentrations are as follows. We're told all of the concentrations, and we're being asked just to simply calculate KEQ. We, of course, know that to calculate KEQ, that's going to be the products over the reactants. In this case, just the one reactant, Li2CO3. Each raised to the powers of their stoichiometry. That's why Li2 plus will be squared. There's a 2 in front of it. And everything else is to the 1, which we don't necessarily need to write out. Once we have the equation set up, we just plug in our values. On top, we have 0.2 squared times 0.1 all over 6. Let's plug this into our calculator. We have 0.2 squared times 0.1. All of that divided by 6. We see here that this is equal to 6.67 times 10 to the negative 4. Recognize all I did was see that it was just repeating 66666. So I just reduced it to 2 decimal places when in doubt. Do I need any units? No. Equilibrium constant is unitless. It's just a number. Any questions on either one of the left questions that we just did? Okay. Let's now do some Le Chatelier's principle. Problem 3, all of problem 3 is explicitly about Le Chatelier's principle. So allow me to just carefully review Le Chatelier's principles one more time before we jump into it. Hopefully you either have your copy of the handout or at least your written table from Monday's lecture. The way how to read this table is, of course, column by column. So it goes, if we add reactant or product, we will shift away from the reactant or product. And the last column explains why. So we're going to zoom in over here to focus on what we need to look at. So if we add a reactant or product, we will need to shift away from that reactant or product. If we remove a reactant or product, the equilibrium will shift towards that reactant or product. If we increase pressure, we will shift towards fewer gas molecules. How do we know if something has fewer gas molecules? Remember, that'll be based on stoichiometry. If we decrease pressure, we will move towards more gas molecules. And the last condition is changing temperature. If we increase temperature, we favor the endo direction. Remember that the endo direction is positive. If we decrease temperature, we favor the exo direction, which of course is negative. These are the big 3 categories that I can ask you when it comes to Le Chatelier's principle. I'll either ask you what happens when we change temperature or pressure, or maybe having something to do with the chemicals involved. Let's do the first question together. Now, this question, as written and is presented in this format, looks very overwhelming. I mean, if you were to think about this another way, there are 1, 2, 3, 4 columns, 1, 2, 3, 4, 5, 6, 7 rows. That means that there is 28 points in this one table. 28 cells. Each of these cells requires an answer. So technically speaking, this question could technically be worth 28 points. But it's important not to get overwhelmed by this structure, because equilibrium is really about predicting. And with predicting, there is very clever or efficient approaches. What do I mean by that? Well, looking at the different stresses, we see our 3 categories. I'm going to change temperature, I'm going to change pressure, and I'm going to do something with the chemicals involved. What I can do and what I will do is I will first work on the shift column. What do I mean by that? I mean, based on the stresses, I am going to predict what direction the equilibrium will shift. To help me, the very first thing I'm going to do is I'm going to analyze the reaction at hand. First, looking at the energy of the reaction, we see here that it is a positive energy. Since the US education system tells us we read from left to right, that is what tells us this reaction is endothermic to the right. Remember, we read from left to right. So this will always be to the right. The question is, what is the sign? The sign is positive. That means that it is endo to the right. The other thing that we can very quickly identify from this reaction is the number of gas molecules on either side of the reaction. However, a close inspection actually tells us there are actually no gases at all on either side. We're not quite sure how that's going to help us, but pretty good to just make a note of it. 0 gases on both sides. Okay. Now, like I said, we are going to focus on the first column, the shift column first. We're going to look at the different stressors and we're going to predict the direction of the shift. Straight off the bat, a trick question. What happens when we add sodium hydroxide? Well, according to the reaction, sodium hydroxide is a solid. So will it have an effect on the shift? No. Remember, solids are not included in our conversations. So you will just write either an X, you can write a dash, or you can simply write an A. Whichever one you want, I'm going to draw the 3 options. You can either write an X, a dash for blank, or you can just write an A. Whichever one you write, that tells me you understand no effect. Just don't leave it blank. If you leave it blank, meaning if you just left it as is, that would be incorrect, even if you knew internally, well, it's because I left it blank because there's no effect. No, I do need to see some notes. Right, X, a dash, or an NA for not applicable. So I'm just going to use an X just to make it simpler. Next, it says add sodium chloride. Now, technically speaking, as we look through the reaction, there is no sodium chloride. But what do we know about sodium chloride? We know that sodium chloride has Na plus in it. Okay, so we are adding a chemical. All right, let's refer to Le Chatelier's principle. It says when we add a product, we shift away from that product. So let's look at what I wrote on the board in my laser pen. We are adding a product. I've circled the product. We are shifting away from that product. That is what tells us when we add sodium chloride, we'll shift to the left. So we simply draw a left arrow. All right. Next up, now we're adding KOH. Well, same thing as before. There's no K present, but KOH does have OH minus. So yet again, we are adding a product. Guess what we're going to do? We're going to shift away from that product. Yet again, this is to the left. Okay? Next up is an increasing temperature. Now let me bring up Le Chatelier's principle right here. I'll show you. When we increase temperature, we shift towards the endo direction. Didn't we already decide what direction endo was? Yeah, we spent a few seconds at the beginning. So if increasing temperature favors endo, and endo is to the right, then we just simply write a right arrow. Decreasing temperature. Now, there's a really clever way to figure this one out. Because think about it this way. If increasing temperature shifts to the right, shouldn't decreasing it have the opposite effect? And what's the opposite of right? To the left. So we could very quickly figure out the effect just because we identified one of them. But let's take a second to confirm it for ourselves. According to Le Chatelier's principle, if we decrease temperature, we favor the exo direction, the negative. Remember, we saw this way back in thermochemistry. Positive and negative just have to do with the direction. So if positive is to the right, negative must be to the left. So decreasing temperature favors the exo. In this case, exo is to the left. That's how we confirm that we've drawn the correct arrow. Finally, we have increased pressure. According to Le Chatelier's principle, increasing pressure favors fewer gas molecules. But we already decided there are no gases at all in this reaction. So let me ask you, is pressure going to have an effect? No. So all we write is an X. And if increasing pressure has no effect, decreasing pressure also has no effect. Remember how we just worked through that. When we talked about adding chemicals, we specifically looked at the reaction. To understand temperature, we first identified endo or exo. To identify changes of pressure, we identified number of gases. So taking a few seconds at the very beginning to understand, is this endo, exo, how many gases, helped us in the long run. Now we're not done yet. We've only finished the first column. We have predicted that in response to these stresses, the reaction will shift to get to equilibrium. We now have to predict the effect the shift will have on these chemicals. Starting with sodium hydroxide. If we add sodium hydroxide, there is no shift. So is there going to be any effect on the sodium hydroxide? No. So X. The same thing can be said of the other chemicals. Adding the sodium hydroxide had no effect on the reaction at all. So it has no effect on the chemicals at hand. All right. Let's do the next one. When we add sodium chloride, remember, we already discovered this. We already know that adding sodium chloride shifts the reaction to the left. When we say shift to the left, what that literally means is we are making reactants and we are using up our products. In other words, when we shift to the left, we expect our reactants to increase. We expect our products to decrease. So when we shift to the left, our two products, we expect to decrease. So you would draw two down arrows. Will adding sodium chloride have an effect on the sodium hydroxide? Let me say that again. Will adding sodium chloride have an effect on the solid sodium hydroxide? No. Solids are not included in our conversation or calculations. This is actually going to be an X. So guess what we can do immediately? Since this is all about solids will have no effect. I'm going to immediately write X's for all of it. Immediately. What else can I do very quickly? Well, don't forget, pressure had no effect. Had no effect on the shift. So just like sodium hydroxide up here, X's all the way around. All right, now watch this. Here's a little trick. The next row we're doing is adding potassium hydroxide. When we add potassium hydroxide, we're going to shift to the left. Wait a minute, didn't we just do this? Yeah, we just spent time figuring out that for the above stress also shifts to the left. Don't we already know what those effects are? We don't even need to think about it. I'm just going to copy those arrows back. All right, let's talk about increasing temperature. Oh, wait, now look at this. This is shifting to the right. That is the exact opposite of shifting to the left. So in theory, shouldn't the effects also be opposite? Up, up. Let's think through that. When we shift to the right, what that literally means is we are making product. When we shift to the right, we use our reactants. In other words, we expect our products to increase and our reactants to decrease. Of course, in this case, the reactant is a solid, so no effect no matter what. But the products will both increase. Last row, decreasing temperature shifts to the left. Oh, wait a minute, I just saw this. Right up here and right up here. And I already know from those two, the products decrease. I'm not going to waste any time. I'm just going to write those down arrows. And just like that, we have completed this 28-point table in 12 minutes. And that's with me talking it through, spending time on little nitty-gritty details. The point I'm trying to make here is don't let these tables intimidate you. There are clever and efficient ways to work through this. Let's do the other one together. The first thing we are going to do is we're going to analyze the given equation. We're going to spend a couple minutes or seconds identifying endo, exo, and gases. According to this equation, the energy of the reaction is positive. That is what tells us this will be endo to the right. Remember, we read in the US education system from left to right, so it will always be left to right. It doesn't matter if it's endo or exo, left to right. Right now we can look at the gases. Okay, well, technically speaking, every chemical here is a gas. On the left-hand side, we have in total 4 gases. Where does that 4 come from? 3 plus 1. Remember, number of gases comes from stoichiometry. We have in total 4 gases on the left. How many gases do we have on the right then? 2. All right, so this is in fact a case where there is a different number of gases. So we can even go ahead and say that the right-hand side is fewer and the product side has more gases. We don't know exactly how this will help us, but we trust that it will help us. All right, now we're going to look at these rows. Now, this is even bigger than the first one. This is 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is actually 40 cells, 40. So in theory, this is an entire table is worth 40 points. Don't let that intimidate you. Work through it systematically. The first thing we're going to do is the shift. All right, let's go one by one. You have Le Chatelier's table near you. The very first thing is if we add N2, if we add a chemical, we shift away from that chemical. That's going to be to the right. If we add a chemical, if we add H2, we shift away from H2. Yet again, this is going to be to the right. Once more, we're adding another chemical, but this time, it's a product. When we add a product, we shift away from that product. So in the completely opposite direction to the left. You see, we're making predictions. When it comes to Le Chatelier's principle, we're not necessarily calculating much. We're making assumptions and educated guesses about how the reaction will proceed to get to equilibrium. What if we remove a chemical? Now this is removing. All right, so now that's the second row of Le Chatelier's principle. Let's look at what it says, just to be sure. It says if we remove a reactant or product, we will shift towards that reactant or product. So when we remove N2, here I've just drawn it with an X to make it clear we're asked to remove it, we will shift towards N2. This means we will shift to the left. We're being asked what happens when we remove H2. Again, we shift towards that H2. Yet again, this will be a shift to the left. Finally, when being asked to remove NH3, all right, this one's actually on the product side. Which way are we going to shift? We're going to shift towards the products. This will be to the right. Next up is temperature. Remind ourselves what the effect of temperature is. According to this, increasing temperature favors endo. So if we increase the temperature, we favor endo, which we've previously established as being to the right. And here's one of those nifty tricks. If increasing temperature shifts to the right, decreasing temperature must be the opposite. Prove it to yourself. Next up, we have pressure. Okay? Let's remind ourselves of what it is. It says increasing pressure favors fewer gases. Okay, didn't we spend a second to identify which side is fewer? Yeah, we did. Increasing pressure favors the fewer side, which is to the right. And check this. Once we know increasing pressure favors the right, the opposite, decreasing, must favor the left. With that, I have completed the shift column. Now we're going to work through this systematically. And the best way to do this is to arbitrarily pick two rows of opposing directions. It doesn't matter which two rows you pick. Just be sure they're opposite directions. You could have picked the one I did on the in green. You could have done the increased pressure. You could have even done the increase and decrease temperature. Just pick two rows that are of opposite arrows. Let's spend time working through it. When we shift to the right, we make product and we use our reactant. That means we expect our products to decrease. I'm so sorry. We expect our products to increase when we make it. We expect our reactants to decrease. Our two reactants, N2 and H2, will both decrease. Our product, the NH3, will increase. Now, here's the beautiful part about taking our time at the beginning. In doing so, we know exactly what arrows or directions are needed if we shift to the right. We have a couple cases that shift to the right. Shouldn't they be the same arrows? Tell you what, why don't I just copy these arrows over and over and over again for everything that shifts to the right? Boom. All right, now let's do that other arrow. Now here's another opportunity to get through this with efficiency. If shifting to the right leads to these arrows, then shouldn't shifting in the opposite direction lead to opposite arrows? Yeah. Up, up, down. If you're feeling unconfident, prove it to yourself. Why not try it your way? Why not try it your way? Let's try it again more in depth. When we shift to the left, we are using products and we are making reactants. When we use products, they are expected to decrease. When we make reactants, we expect it to increase. And that is exactly what we predicted. And just as before, since we've taken our sweet time to know the effects for to the left, I can just copy those arrows right back. And that's it. A 40-point question completed in less than 10 minutes with professor commentary. Do not let Le Chatelier's principles scare you. You're making predictions. It'll either shift left or right, or the amounts will either increase or decrease, or in some cases, no effect at all. Do we have any questions on anything we've done so far in today's workshop? Okay. We'll call it for today in terms of our recording.